Hello, and thank you for attending today's webinar. This is Joel Smith with the Statistics Division. I'm going to introduce our speaker today. Our speaker is Lou Johnson with Minitab Inc. Lou is a technical trainer and former master black belt. He has degrees in chemical engineering and statistics, like I know a lot of our members have as well. Today, Lou's going to be presenting on sampling plans for extended gauge R&R. This was a very popular talk at this year's ASQ World Conference, and we're now happy to be able to share it via webinar with the division. If anyone has questions during the webinar, all phones have been muted except for the presenters. So please use the questions interface in GoToMeeting, and I will hold those questions until the end of the presentation, at which time Lou will have time to answer everything for us. So for now, I'm going to go ahead and turn things over to Lou, and thanks again for presenting for us today, Lou.
My pleasure, Joe, and thank you very much for that introduction. The webinar this afternoon is called Sampling Plans for Expanded Gauge R&R Studies. This webinar was given by Daniel Griffith and myself at the ASQ World Conference, as Joel mentioned. Now, when I think about the expanded gauge R&R and the value or the importance of being able to carry out one of these types of measurement system analyses, I think of Volvo. I spent a little bit of time at a transmission and diesel engine manufacturing facility for Volvo in Hancock, Maryland, a few years ago. And there were a couple of things that really struck me about this manufacturing facility. Some things I could describe to you about the plant was extremely well organized. It was extremely clean, very well automated, and oh my gosh, was it big. It was huge compared to a lot of the other manufacturing facilities I had been in. In touring the plant, I was discussing with the quality manager of that division what is really critical, what are the key components of manufacturing a diesel engine that you intend to run 3 million miles. I mean, that number just blew me away, that their goal was that these engines were typically supposed to last 3 million, 4 million miles as an average reliability. I thought that was a fantastic reliability. So I asked him, I said, how do you guys do that? And he said, well, you might not believe it, but one of the most important aspects or most important quality performance measures that we have on how our manufacturing facility is working is the torque of the bolts that we insert in hundreds of different places within these engines and within these transmissions. What he told me was that if we don't get exactly the right number of bolts with exactly the right torque on them so that it will do the job that it's supposed to do at that location, we're going to have a negative impact on the quality of and performance of that engine. And what I thought about when he said that was how would the measurement system analysis for that torquing system or torque measurement system, how would that look? How could you possibly consider all the dozens and dozens of different torque wrenches, or essentially meters, that are located throughout the plant, the dozens and dozens, if not hundreds, of operators using those measurement devices, the torque wrenches, and then finally the parts, the different types of nuts and bolts that they had to go ahead and apply this measurement to. So they recorded every single reading for every nut and every bolt that got tightened in that facility, and here the quality manager was telling me that that was key to their performance. What struck me upon hearing that was that that measurement system is going to require an expanded gauge R&R, not your typical gauge R&R that would look at the part and the operator as the two main components of variation, but also in order to be a complete study and a definitive study, it would have to have what? It would have to have the gauge as another component. Now, since that time, I've worked with dozens of companies making all sorts of products, from mattresses to to electronic equipment, to pumps, to chemicals, to adhesives, and so on. And in each one of these scenarios, what was clear to me was that they were not going to be able to do a comprehensive analysis to do a complete capability assessment of their measurement system unless they were able to add that third component, the third component being the gauge, to their total sources of variation. So that's what we're going to talk about today. We're going to talk about an expanded gauge R&R, and in particular when your expanded variable is the gauge that you're using to measure. The agenda for the day will look as follows. I hope I've clarified a little bit about the dozens of different industrial applications of the expanded gauge R&R and why being able to execute an expanded gauge R&R is so critical in a lot of different manufacturing measurement systems and laboratory measurement systems. We're going to do a comparison of the standard gauge R&R versus the expanded, and in doing that comparison, what we're going to have to do is we're going to have to take a step back and really dissect a standard gauge R&R and look at all the different parts of it, ask ourselves, what is the goal here? What are we trying to do? What are we trying to measure? Why do we have the data collection plan organized the way it is now for the current standard gauge R&R? Because we're going to have to apply those same principles when we're going to make our decision about how to change the sampling plan for an expanded gauge R&R, but continue to measure the same key outputs from that any gauge R&R that are critical. We'll be going over an example of an expanded gauge R&R, one done on gas chromatography columns by a local company here right outside of State College, Pennsylvania. We'll talk about their measurement system and their sampling plan they used, why the number of parts ends up being critical in some of these studies. We'll talk about how to think about the number of parts and what is the role of the number of parts in the studies. Then we'll wrap up that particular case study and talk about the positive results that they achieved by implementing the results of their expanded gauge R&R. And then finally, we'll talk about a little bit of an empirical experience that I've had dealing with these interaction terms that are going to take place in expanded gauge R&R. Now, at the end of that, we'll have laid a great foundation for really understanding what the components of a gauge R&R have to do in order to estimate the values that we're looking to estimate for any gauge R&R. Based on that understanding, we're going to take a step back and say, all right, now how can we implement a new sampling plan for an expanded gauge R&R, which in no way will resemble the standard plan multiplied by, say, 3 gauges, which is what you might expect, and frankly, which is what most of our clients would use whenever they had a first swipe at their expanded gauge R&R. They would say, the standard plan works fine, so I have 3 gauges, I'm just going to multiply it by 3, and that'll be my study. That would be somewhat effective, that would work, but it would be far from being the most efficient study that you can put together. So what we'll do is we'll talk about how many repeat measurements do you need to estimate the repeatability of the gauge. We'll talk about the impact of the number of operators you choose to study, the number of parts you choose to study, or the number of gauges you choose to study in your sampling plan, and what impact that will have on your final results and the precision of those final results. We'll talk about the size of the variance components that you intend to measure, how it's important to match the sampling plan to the size that you anticipate that specific variance component having, and then finally we'll get to the final answer. The goal for today is to recommend to you a sampling plan for an expanded gauge R&R as applied to your whatever measurement system you hope to apply it to. So let's start off with the standard gauge R&R. We're going to focus a little bit on what I know is going to be review for most of you, but a standard gauge R&R as identified in the Automotive Industry Action Group's standard manual for measurement system analysis is going to be to take 10 parts, have 3 operators measure those parts, and then repeat that measurement for a total of 60 readings total. What you learn from those 60 readings is how much variability is coming from your measurement that we commonly call your measurement gauge, or the instrument as I call it. We call that the repeatability. How much is coming from consistent operator-operator bias? How much is coming from the interaction term between the operator and the individual parts you're measuring? And then the fourth component of variation would be how much part-to-part variability do you have in those 10 parts that you chose to run your study with. So that's kind of a summary of a standard gauge R&R. If I could kind of reiterate that, if we look at a data set for a standard gauge R&R, here are 3 operators. Daniel, Kelly, and Andy are going to take our 10 parts that they're measuring. They'll measure the density, in this case, of those 10 parts in a random order, and then we'll ask them to repeat those measurements again. And so we'll end up with 60 measurements. We will note that if you have missing measurements, Minitab itself as a software will not allow you to execute the analysis of your gauge R&R. If you have one measurement missing, it will give you an error message, and then if you try to sidestep that error message and go to the GLM, which you can analyze the gauge R&R out of the standard general linear model dialog box, that will also give you an error message if you're missing both replicates of that one operator by part combination. So missing values are a problem with standard gauge R&R. Once again, the goal is very simply to estimate, to take your overall variation, all the variation in your study, and break it up into 4 component parts. How much variation is coming from the different parts? How much variation is coming from the gauge itself that we call the repeatability? How much consistent operator-to-operator variation is there in my measurement system between operators? And then a little bit more subtle estimate of operator variability, which is how is the way that each operator is interacting with specific parts, oftentimes unique parts that we have in our process, causing that fourth source of variability, the operator by part interaction. So as complicated as a gauge R&R might look, it's important to remember there's really only 4 numbers that we get from a gauge R&R. We get sigma part, sigma repeatability, sigma operator, and then sigma operator by part interaction. Those four measurements are what we are trying to achieve. And of course, we need to remember that those measurements are just estimates. And the amount of variability in those estimates will be a function of the way we execute our sampling plan, which sampling plan we chose to execute. The measurements that we chose to take will have an impact on the variability or the precision of the estimates of those 4 standard deviations, which is our goal. Now, we never really see those standard deviations. Here we see some equations around those variance components. Once again, the breakdown of the total variability, the chart that you saw earlier, which is a good overview of what a gauge R&R does, we would summarize that mathematically by simply saying that the overall variation is the sum of the variation from the parts, the operator, the gauge repeatability, and the operator by part interaction. So here we see this equation as what's going to happen, or what the analysis of variance, how that table is going to break down when we break down those variance components. Of course, we combine these and give them certain names. We call them the repeatability and the reproducibility, and then finally the total measurement variation is the sum of the reproducibility and the repeatability that we call sigma squared measurement. What we do with those estimates of variability is we combine them into certain ratios that give us a sense of the capability of the measurement system. The three common ratios that we use are the percent study variation, which takes the measurement variation and divides it by the total variation within the study, the percent tolerance, which takes the same value in the numerator and divides it by the amount of variability your customer will allow you to have, which is the spec range, or sometimes called the tolerance range, and then finally a mirror image of the percent study variation is to use the percent process variation, which simply uses sigma historical as your part-to-part or total variation estimate instead of the 10 parts that you used in that study. Very important to remember these three, and also to focus in on the fact that only one of these measurements, sigma or standard deviation, percent study variation, is a function of sigma total, which is a function of sigma part. So you need to think about the fact that the variation from part to part in your study goes into the denominator of the percent study variation calculation. The percent tolerance calculation, on the other hand, is independent of the sigma squared part, and the percent process is also independent of sigma squared part for the 10 parts that you chose for your study. That aspect of percent tolerance and percent process variation is going to come in handy a little later in our talk. We'll come back to that. Now let's look at an expanded gauge R&R. If I was to look at the sampling plan for the expanded gauge R&R that we're going to use when we look at this gas chromatography expanded gauge R&R as our case study to illustrate the expanded gauge R&R, what we're going to do is we're going to take one part, we're going to ask an operator to measure it on one gauge, and then we'll ask that operator to do two measurements, two repeat measurements. So we're looking for each of the combinations of part, operator, and gauge to be measured twice for each combination. Now in their particular study, they chose to use 4 parts, or columns as we're called for gas chromatography columns. There were 4 operators that were used in the study as a representation of all the operators, or I think I may have called them technicians a little bit later, that were working within this facility, and then we chose 4 gauges randomly from the dozens of gauges that they use to measure all these parts. So this is what the layout for an expanded gauge R&R might look like. And then based on the results of that style study, we're now going to have 7 components of variation that we're going to estimate. So we're going to estimate 4 that we've seen already with the standard gauge R&R, the part-to-part variation, the repeatability within one given gauge, the operator-to-operator variability, and the operator-by-part interaction variation will still be an output from the expanded gauge R&R study. What we've added to that study, those 4 components of variation, are 3 more, the gauge-to-gauge variability, the part-by-gauge interaction, and then the operator-by-gauge interaction. So we now have 7 components that we're going to measure instead of 4. So that's one of your key differences. The way we're going to break that down is we're going to look at a base case for a sampling plan that you might choose to use, which would be what? Which would be to take a standard gauge study, a 10 by 3 by 2, multiply it by 3 gauges. Obviously, if 3 was the right number for the number of operators, you might guess that 3 would be the right number for the number of gauges, and what we would end up with would be using 180 measurements, 3 times 60, it would be our total study. That's going to be our benchmark study. That study would work if you can afford 180 measurements. Now, whether or not that's the most efficient study, that remains to be seen. That's the goal of this work. So we're going to use 180 measurements, 10 by 3 by 2 by 3 as our benchmark, and try to compare some alternative sampling plans to that. Now, one thing I'll point out is that the result of your expanded gauge R&R will most likely not be percent study variation because of that dependence on the number of parts that contribute to the variation within that calculation estimate, the estimate calculation. We're going to choose not to focus on percent study variation, but instead focus on percent process or percent tolerance. Finally, if I was to summarize the differences between the two, an expanded study allows you to add that additional factor. As I've mentioned, Gage is the most common additional factor to add to your study. We'll get the interactions of that factor with the operator and part will also be assessed. The expanded gauge R&R will allow you analysis of missing data points, even if you're missing both replicates of any different combination of operator by part by gauge. And then finally, the key here is that 180 reading sampling plan will most likely be far too large to be useful. So we're going to have to think about a way to reduce that down to try to meet our budgets. And the most common way to reduce that down is typically to reduce the number of parts. That's the most effective way, but we'll get to that. I jump ahead a little bit there. We'll get to why that is so a little bit later on. Now let's look at a case study. Let's look at a company that implemented an expanded gauge R&R, this gas chromatography manufacturing, gas chromatography column manufacturing company outside of State College, Pennsylvania, manufactures these gas chromatography columns that are used in thousands of different industries whenever measuring a trace amount of some compound is important, and especially when the real goal is to assess the amount of that trace amount of compound that's in a mix of just an unbelievable mix of different types of compounds, and all you're interested in is the one flavoring, the one pesticide, the one small active ingredient within a pharmaceutical, and so on. So the manufacturer of these gas chromatography columns was very much interested in their expanded gauge R&R, and the reason for this is that the measurement of the performance of the column was critical to their manufacturing, because it was so critical to the performance at the customer. When they would manufacture the column, this is an extremely expensive and extremely high requirement piece of equipment that has to perform exactly the way their customers need to, or they'll end up getting mistaken readings of the amount of whatever trace chemical it is they're trying to measure. So in the manufacturing process, one of the steps is to measure every single column with a standard mixture, and then see if the column is performing as we know it should perform on that standard. Based on that one reading, we're either going to scrap that column and we lose all the potential profit from selling it, or we're going to have to rework that column if we think we can bring it back to good performance. So that measurement ended up being critical. If they take that measurement and the measurement is out of spec because it's a bad column, well then, congratulations, we did what we're supposed to be doing. We eliminated a poorly performing part from getting to our customer. On the other hand, if that part was out of spec because of an issue with the measurement, the technician, the gauge, or just within gauge variability, then that's not necessarily a job well done. We need to know if that variation is contributing to whether or not we're rejecting or failing to reject parts. So this measurement system and understanding the system was critical to this company. They ran an expanded gauge R&R. They used 4 gauges, or chromatographs, as we call them here. They used 4 technicians, or 4 operators, and they used 4 parts. Now, in this particular sampling plan, it's interesting. They selected 4 parts for physical reasons, for time constraints. They wanted to keep all of the operators and all of the gauges going at the same time, and they wanted them all running in parallel. That would reduce the size of the study time-wise by a factor of 4. This was a very long and a very expensive measurement, and they wanted to try to finish the study up in a reasonable amount of time. So they chose 4. For one key reason they chose 4 was just to keep all the operators and keep all the chromatographs going and working at the same time in parallel. The results of their study were extremely valuable to them. They were able to determine, number 1, the percent tolerance for their measurement system was way out of line with what we would consider a good system, way above the 30% kind of benchmark that we say a good measurement system must be less than. Now, you'll notice I'm completely ignoring percent study variation. They didn't take any care or preparation into making sure the parts represented the natural variation in their process, because they planned to completely ignore percent study variation and focus just on what? Just on percent tolerance, because that's what they were using these gauges for. Not only did we learn that the percent tolerance was beyond what we needed for the measurement system to show, it was almost at 50% of the customer's spec range. We also learned why. We learned that the repeatability of the gauge was a major hitter at about 30% of tolerance, and that the gauge-to-gauge variability was also a major contributor at about 30% also. So if I was to prioritize which sources of variation in my measurement system would give me the greatest return on my investment of trying to remedy those sources of variation, I would say the repeatability of the instrument and the gauge-to-gauge variation are the way to go. Now, there was operator-to-operator variability. The tech variability there is reasonably high and was statistically significant at 18%. So is the part by gauge interaction at about 7.3%. However, we're going to choose to lower those in our priority of responses to this study. We're going to focus on the big hitters. A graphical output of this study is seen here, is seen in the meter-to-meter variation is the stronger of the 2 components. The tech-to-tech or operator-to-operator variability is definitely there, and but at a lower level. Now let's have a look at what they did with the results. They decided that the gauges need to all behave the same, so they implemented a program to standardize or calibrate the gauges all to the same calibration standard. This takes a lot more time to do, but is more effective in that it brings all the gauges together and minimizes the gauge-to-gauge variability. They had to make modifications to the instruments to try to improve the repeatability of the instruments, and that definitely they were successful in that. And then finally, it was interesting, one of their follow-ups is what they did not do. What they did not do was implement a new automated injection system. They thought that their operator-operator variability was the biggest source of variation, and injection was the strongest component to that operator-operator variability. When they saw that it wasn't their biggest component, they went ahead and lowered that as one of their more expensive and wasn't going to be necessarily successful approaches to reducing the measurement system variation. The benefits were a 60% drop in their first pass rejects. This decrease in the number of columns they had to measure twice and rework and so on increased the capacity of their quality assurance department, and then that, of course, decreased the measurement costs. So this is an example of an extremely valuable learning that they had in executing their expanded gauge R&R, and the profitability when they implemented their results. Now we're going to finish up this case study with a comment. This is an empirical observation. I've worked with at least 40 different companies in implementing their expanded gauge R&R, and my experience has been pretty consistent, almost unanimous, in that the interaction terms, whereas they were often statistically significant, they were very, very rarely a key driver, that the interaction term was the main focus of what they learned in the study. And secondly, I wasn't surprised by that. As an engineer, if I was to think about maybe an operator by column interaction at that company, that gas chromatography company called ResTech here, or think about a solution by pH meter interaction for a chemical company that we worked with, I would have guessed that there wouldn't be an interaction. So it wasn't surprising at all to me to learn that that interaction didn't happen. The idea that the interactions are of lesser importance is going to come into play when we go to the next step of our discussion, which is how do we decide which sampling plan is the most effective sampling plan, to implement. So let's go on to the next part of our discussion. We're going to talk about the sampling plans. How does the data you choose to collect and what you choose to sample, how does that affect the precision and the accuracy of your results when you finally implement that sampling plan and read your gauge R&R results? So let's have a look at the goal again. We need to go back to the heart of what we're doing, and we're going to have to prioritize. We're not going to be able to do a great job estimating all 7 of these components. We're going to have to prioritize, and the first thing we're going to do is we're going to say that we're going to eliminate the need to measure the part-to-part variation. We're not going to use percent study variation, and that decreases the priority of measuring very, very precisely how much part-to-part variation do we have in our process. So that's going to lower in priority that one component that we want to measure in this study. We're also going to lower in priority the 3 interactions. We just mentioned that the interactions, in most situations where the 3 components of variation are random variables, it makes perfect sense that those interaction terms will be the smaller contributors to our overall variation and not the larger contributors. That leaves us with 3 sources of variation. Our sampling plan should do an excellent job of measuring the repeatability within an instrument, within a gauge. It should do an excellent job of measuring the gauge-to-gauge variation, and then an excellent job of measuring operator-to-operator variation. So this is where we're going to focus, and we're going to focus on the repeatability or the within-gauge variation first. Now, in focusing on the repeatability or the within-gauge variation, there's a very important aspect of your sampling plan that you need to know in deciding how many repeat measurements do I need to use to estimate the repeatability or the within-gauge variation. The within-gauge variation is independent of how many parts you choose, how many operators you choose to study, and how many gauges you choose to study. The only factor that influences the precision with which you estimate the repeatability of the instrument is how many times you take the exact same combination of part, operator, and gauge, and how many times you measure that at least twice and answer the question, did I get the same answer twice? If I did, I have good repeatability within the gauge. If I get widely different answers, then no, I don't have good repeatability. So what we call the degrees of freedom, the number of parts, number of operators, number of the gauges, times the repeats will determine your degrees of freedom, will determine the precision with which you estimate the within gauge variability. And not only do we know that that is the only determinant, but we also know exactly what the relationship is between the degrees of freedom that you use and the precision shown here on the y-axis of that estimate. So what we're going to do is we're going to go to a paper published by Yangling Zhao here at Minitab, and what she studied, or what she was able to demonstrate mathematically, is that you can estimate, or you can measure mathematically the percent accuracy of your estimate of the within gauge repeatability as a function of how many degrees of freedom or how many repeat measurements you make, and you end up with the blue curve here. And what we're learning from the blue curve is three things. The more measurements you make, the more repeat measurements you make, the lower the variation in your estimate, number one. Number two, that benefit kind of tapers off. At some point, it keeps going down as you take more parts, but you would hardly consider taking 50 parts, the benefit of taking 100 parts versus taking 50 parts, as the difference in these two y-axis readings of at these 2 points as being worth doubling the number of repeat measurements that you take. So at some point, you reach the point of diminishing returns, and what we're going to estimate that to be is somewhere right around 20%. So whenever you get within plus or minus 20%, it's a little bit subjective. We're going to choose to use 20%. And what we're going to learn is that if you can use between 35 and 45 repeat measurements, in other words, that many degrees of freedom, that will give you a reasonable estimate of your within gauge variability. Now that's a very important number to know, because that's setting your baseline for the absolute minimum number of combinations of part, operator, and gauge that you must have in your sampling plan to do a reasonable job of estimating the gauge repeatability. Now what that combination turns out to be, it doesn't matter. It's the repeats that are critical. So let's look at our standard study. Let's look at our standard study at 10 by 3 by 3 by 2, those 180 measurements. Those give us 90 degrees of freedom with which to estimate the repeatability. That, according to our last graph, is more than we need. So when we make the suggestion that you could consider reducing the number of parts from 10 to 5, giving you 90 measurements or 45 degrees of freedom, which is plenty to get a reasonable estimate, you would say that this reduction from 10 parts to 5 parts is a worthwhile trade-off, is something that you would consider doing. Now you might say, well, what happened to my percent study variation estimate? I did a worse job of estimating sigma part, therefore I've made my percent study variation estimate less precise, but I'm willing to trade that off because I've already dismissed percent study variation as one of my key capability measures when I can use percent tolerance instead. So knowing the degrees of freedom to estimate the repeatability turns out to be a valuable benchmark from which we can move forward. So we're gonna not consider worry about how many parts we measure. We're going to go ahead and take the reduction in the number of measurements down to 90 as a reasonable way of doing business. Now, what we turn to next is the fact that we still don't know whether 3 was correct for the number of operators or 3 was correct for the number of gauges. So now we're going to turn our attention to the number of operators we choose to study and the number of gauges we choose to study. Before we go to the simulation, what I'd like to point out is that operator and gauge are identical. So we're going to do a simulation that considers changing the number of operators and the role of the number of operators in estimating sigma operator but the mathematics will be identical to sigma gauges. So once we do this for sigma operators, we're going to say the exact same logic applies to estimating sigma from gauge to gauge. Now to do that, you have to understand the simulation. We're going to start with a three-factor random effects model for each observation being modeled as a constant, a mean value, plus a contribution to the overall variation by the part that we measure, the operator who measures it, the gauge they use to measure it, and then the fact that every gauge has a certain amount of inherent repeatability. We'll have that fourth component of variation, which is sigma repeatability. So once again, our goal is just four components: sigma part, sigma operator, sigma gauge, and then sigma repeatability or within gauge variation. The way the simulation works is that just as all simulations work, we're going to implement a known level of variation for each of our four components. In other words, we get to set the computer program, we get to dial in what standard deviation we're going to use for all four of those variation contributions. We go ahead and use this model and the standard deviation that we chose to implement, and then we can simulate a set of data. So we're going to simulate a number of samples that we're going to take, and then we're going to go ahead and generate that data based on those known values for those standard deviations. You simulate the data, and once you have the data, then you can run your gauge R&R, just as if you walked out on the plant floor and executed the gauge R&R on the plant floor. The only difference is we executed it with a known level of variation for each of our four components. We're going to then use the results of that gauge R&R to estimate those four standard deviations shown here, and then we can go back and do it again. So with the computer, we can do this as many times as we like. We're going to do it 5,000 times, and the way we're going to judge the quality of that sampling plan is really very simple. We look at all 5,000 answers to what the gauge R&R said our sigma should have been. We compare it to what we know the sigma was for the data generation, and we see how close the two match up. If the two match up very closely with low variation, we say that's a great sampling plan. And if we see a lot of variation around the known level, the true level, and we see that the average of all those 5,000 readings was biased compared to where the true level should have been, then we're going to say that's a very poor estimate. That's a poor plan because it didn't do a good job of estimating the answer that we knew ahead of time it was supposed to get. So what we're going to do is we're just going to focus on sigma operator, but focusing on sigma operator will allow us to understand how the simulation works. We're going to focus on sigma operator. We're going to estimate sigma operator 5,000 times using this simulation routine, and then we're going to draw a histogram of those answers to the question, how big was sigma operator, and see how the distribution of those answers focuses on the right answer. So here we see three different sampling plans. The true value that we used for sigma operator was 5. So to generate each of these data sets, we use sigma operator as 5, and then we tried 4 different sampling plans. We tried 2 operators, 3 operators, 4 operators, which are very, very common, typical values used in gauge R&R. And then we tried a number of operators a little bit beyond what most people use for gauge R&R. We tried 8, just to see what the effect of 8 operators was on our estimate. Now, it's very easy to see with 2 operators, the right answer shown here in red is 5. We're getting a lot of variation to the high side and to the low side around the right answer, and but more importantly, we're also not converging on the right answer either. In other words, if I was to ask the question, what is the most common correct answer the most common answer we should get from using 2 operators in our sampling plan, it would not focus on 5. It would focus on a value much less than 5. So here, the end result of only using 2 operators is that what you'll do is you'll be able to estimate sigma operator, but your estimate will not have very good properties. We'll have too much variation around the right answer and also not average the right answer or have the right answer be most common. Now, if you use 3 operators to estimate sigma, it goes a long way. The improvement is dramatic, much less variation, and the average moves much closer to the true value. 4 operators improves it still, but you have to ask yourself, am I willing to spend another operator and all the extra readings that entails in order to get the benefit from here to here? That's a question that only you can answer for your system. And then finally, of course, if we use 8 operators, the center is not biased at all. The most likely answer that we'll get is 5, and we have much less variation around the 5. So what we learned from the simulation is that the number of samples of each component that you're trying to measure has a direct impact on the quality of your estimate of that variance component, of that sigma. We can summarize that simulation by simply looking at the quality or the variation or the error in our estimate of, in this case, sigma operator as a function of the number of operators. Now, there is no one correct answer along this blue curve. You're going to have to decide how many measurements you're willing to spend to improve the quality of the results of your Gage R&R, but this sets the stage for us to try many different sampling plans and then see how well they work. So let's go ahead and do that. We know the effect of degrees of freedom on sigma repeatability. We know the effect of the number of operators on our estimate of sigma operator, and by symmetry, we know then the effect of the number of gauges we study on our estimate of sigma gauges. So we know the impact of each of these sample size counts on the variance component estimate that we hope to estimate in our expanded Gage R&R. So let's put it all together. Let's compare a couple of plans. In order for us to compare a couple of plans, we have to have our known values. So we're going to start out with a system that we set the values for the system as follows. We're going to give the Gage standard deviation a low reading of 1. We're going to give the operator standard deviation a high reading of 5. We're going to give the repeatability within an instrument a value of 1 for our standard deviation, and then we'll put our historical standard deviation at 35. Now, the reason we need the historical standard deviation is that we're going to measure the effectiveness of these sampling plans compared to the known percent process. So we need the historical standard deviation to calculate our yardstick. Our yardstick is going to be the percent process variation calculation, and in this known study, percent process, as we've outlined it here, has a value that it should be. It should be sigma squared for the gauge, sigma squared for the operator, and sigma squared for the repeatability of the instrument itself. Those get summed, and we'll take the square root of that for sigma squared measurement. And of course, we've already set the historical standard deviation at 35. So that's our measurement. We should get percent process equal to 15% for this study. Now we're going to try 3 different sampling plans. Those 3 different sampling plans were specifically chosen to have 2 properties that allow us to learn about sampling plans in general. The first sampling plan takes a lot of samples, 8 samples, and it applies it to the lowest source of variation. So we're taking 8 gauges, even though the 8 gauges, the gauge standard deviation is only 1, is the smallest standard deviation. We do a very poor job of sampling our worst standard deviation, so we only take 2 operators and operators has a standard deviation of 5 that we can set in the simulation. The second sampling plan shoots for the middle, says, well, we'll have 4 operators for the high standard deviation component, 4 samples for the low component of variation, and we'll just see what happens when we shoot for the middle. And then finally, we'll do the best job of estimating percent process, which is to sample the high source of variation quite often so that we have the best precision on our worst source of variation, and we save our worst precision by only taking 2 gauges on our lowest source of variation. So we're going to do the worst job estimating our lowest source of variation and the best job estimating our higher source of variation. Sampling plan number 3 should work the best in this simulation. Now, we already know that that's what's going to happen, but the goal is to try to quantify, well, by how much? We can quantify by how much by remembering slide 27. 2 operators gives you a 90% margin of error on what you're estimating. 4 samples gives you a 60%, and 8 gives you a 40% margin of error. So we know exactly what margin of error to expect for each of these types of size samples. So we're going to put it all together, and we're going to calculate percent process for each of our 3 sampling plans. And just as we expected, when we put the most samples on the highest source of variation, the correct answer was 15. Our answer was a percent process of about 21 or so. This was the closest we were going to get to the correct answer. We didn't do a bad job if we split the difference and just went 4 and 4. And then finally, we got our worst answer. We said 28% was our percent process variation in a worst case scenario when the correct answer was 15. So this is what happens in a worst case scenario where your estimate, we biased it towards the high side. We said, what if we hit your worst case scenario towards the high side for each one of these sampling plans? What we see is the first sampling plan gives you a much worst case scenario than the best sampling plan. So what we're learning from this is that the way you allot your operators and your gauges should correspond to the size of the variation you anticipate is being caused by the operators and being caused by the gauges. So let's put what we learned together. Let's summarize it. Number 1, you need 35 to 40 degrees of freedom to do a good job estimating the repeatability. Got to remember that number. That's a baseline. Number 2, you can reduce the number of runs by reducing the number of parts, and it will not have a negative impact on the estimates of percent tolerance and percent process that you'll get from your gauge R&R. So number 2, we're not going to focus on the parts. We're going to focus more of our attention on more gauges and more operators. Number 3, the more operators or gauges you use, the better your estimate, the lower the margin of error. So that's an important thing to keep in mind. And number 4, you're going to try to match that. So when I answer the question, how many operators should I study, how many gauges should I study, you should ask yourself, which one do I think is the greater source of variation, and therefore a lot more samples to that source of variation and fewer to the smaller source of variation. Now what happens? Many times we'll talk to our clients that are setting up their expanded gauge R&R, and they'll tell us, we don't know. How are we supposed to know our greater source of variation is whether it's operators or gauges? That's why we're doing the study, is to learn that. So the most robust sampling plan that we can recommend would say that you don't know which one is the greater source of variation. Therefore, you'll go ahead and split the difference. You'll use 4 parts, 4 operators, and 4 gauges. Then when you repeat those combinations twice, those 64 combinations twice, your total study will be 128 runs. That'll give you 64 degrees of freedom to estimate the repeatability. That'll be plenty of data to estimate the repeatability, and you focused more of your sampling on the more of your sampling on the operators and the gauges where it counts, where it provides benefit for you, and less on the number of parts where it does not provide any useful information. For those of you who can afford 128 runs, that's the robust plan we recommend. Now, if you can't afford 128 runs, if you'll go ahead and eliminate every other repeat, what you'll learn then is that you'll learn the exact same amount of information about your operator variation and your gauge variation, but you'll still have 32 degrees of freedom to estimate your repeatability, and that will be plenty. And your total number of runs will go down to 96. So this is not a bad plan to go to 96. Now, if that doesn't satisfy you, if you think the repeatability of your gauge is a strong component and you want to do an excellent job of measuring that repeatability, you can reduce your number of parts to 2 parts and cut that down to 64. Of course, your number of repeats will then go down, but you can reduce the number of parts. We list that secondly because there is a notion that your measurement system has to work for all your parts, and we really would resist reducing the number of parts below 4. 4 is considered enough to give you a good enough range within those 4 parts that you can make the case that you studied your measurement system across the full range of parts that you're going to have to measure. So as it turns out, if I had to give one plan that's kind of the universal plan, I would probably say 4 by 4 by 4 times 2 repeats. That would be my best estimate. There are some references here that Daniel and I used to come up with the calculations that we did and used to set up the simulation and so on. And with that, I'll be glad to answer any questions. Joel, I'm not sure if you've been collecting questions or you want to moderate that portion of the discussion.
Absolutely. We do have one question and then another comment. So one question is whether or not expanded gauge R&R would help when there's a difference between supplier and customer inspection. Even though they may be using the same method, obviously results may differ.
Oh, absolutely. In fact, that is one of the most common scenarios. You're having potentially a disagreement with between customer and supplier, and you want to do a comparison between the two. Now, I will say that would be the most complete analysis and comparison of those two measurement systems that you could get. In other words, that's the 100% solution and probably the most expensive solution. If you really were just disputing the average reading, if you were just disputing the average reading, you think their reading always high and your reading always low, much easier to take 5 parts, measure them twice yourself, send the 5 parts to your customer and have them measure the 5 parts twice, and then you can get a paired comparison in that case, a direct apples to apples comparison of just the mean. So that's a shorter, quicker, and dirtier study. But if that's all you need, just comparing the means, then that's a faster and cheaper way to do it than doing the full-blown comparison. Not that the full-blown comparison wouldn't be helpful. Like I said, you'll understand all the sources of variation on their side. You'll understand all the sources of variation on your side, and you'll be able to do a good job of comparing those.
All right. And another comment you may want to just speak to whether you've seen this as well in your experience is that we have a comment that often user has found interactions are often significant when the repeatability is really good.
Okay. And that makes perfect sense, but I'm still going to disagree about the relevance of that. When your repeatability is excellent, that means the statistical significance of a smaller interaction effect is more likely.
All right.
But I agree that statistically it will pop up with a low p-value more often in that scenario. But again, I look at a Gage R&R as more of a descriptive study where you're looking for the big hitters. You're kind of doing a Pareto analysis, and the interaction doesn't turn out to be a big hitter, even though it is statistically significant.
Yep. Someone asked, is there a place where they can run the simulations that you did here? Is that something available in Minitab 16 or?
No, not at all. Daniel Griffith did the programming for those, and that was quite a long, lengthy process, and that is not something that we have just out on the website and easily available. However, if you contact Daniel, he'd be glad to answer any questions, or even test run the simulations or tell you how he did it or so on.
All right. Well, so somebody recommended the book Leveraged Measurement System Analysis by Ryan Brown, Jacques McKay, and Stefan Steiner that discusses ways of reducing the number of parts but keeping a good sense of process variability. So
sure.
That's another one. Just to answer, I realize we're towards the end of time here and people may drop off, so I understand, Lou, you can stay for a couple more minutes, but just a couple of quick things for those that are leaving us. We will make this presentation available on the Division YouTube channel as quickly as possible, hopefully this afternoon. So if you want to watch it again or share it with a coworker or anything like that, you should be able to access it through the YouTube channel. We also have had a few people ask whether or not this presentation can be made available. So Lou, you may want to answer that quickly, and then for those who want to stay a couple more minutes for more questions, we'll remain on, and those who have to leave can go ahead and leave.
Yeah, the slides on the presentation definitely available. Just email ljohnson@minitab.com. I'll be glad to send you a copy of the slides. And as you mentioned, the recording will be available. Finally, Brown, McKay, and Steiner are going to go as far. They've done a lot of work in reducing the number of parts while still maintaining a good sample, and they accurately identify the fact that theoretically, if you're interested in measurement variation estimation, you can do your whole study on one part. That the simulations that they've done always converge on one part as what we know is the right answer. And what happens is we say, well, that's mathematically correct, but it just doesn't feel right to us to study only one part. We want to make sure this measurement system can be used over a range of different parts. So we're going to add a little bit of practical application to our theory about what's happening mathematically, and that's kind of where we came up with 4. But I would agree wholeheartedly that they've done a lot of good work on how to reduce your sample size for a lot of scenarios. They're going to study fixed additional factors and only 2 levels of a factor and so on. So yeah, definitely a lot of good work done by those 3.
Excellent. For those who don't know, since it was asked, the YouTube channel is ASQ Stats Division. So youtube.com/ASQ Stats Division. Another question is there value in doing expanded Gage R&R between 2 different methods measuring the same feature?
Oh, absolutely. Some of the clients that I worked for, one example was a client that manufactured coating materials, and the way they're going to measure the coating was 3 different ways. They're going to measure it with an eyepiece, they're going to measure it with a laser, they're going to measure it with a different drilling kind of study where they drill down to the metal, and then they estimate the slope of the line that's produced whenever they drill out the coating. So very, very commonly used in comparing 3 different test methods. And the benefit of using it for comparing 3 different test methods is that you, as I mentioned earlier, you can compare the supplier's measurement and the customer's measurement, by using a very straightforward comparison of the means, and those 3 test methods that I just described for that coding company could also be compared the same way if you're only interested in the means. But whenever you're comparing different test methods, it's critical that the means match, but also it's very important that you choose the method that has what? That has the lowest overall variation. So I would say that is a perfect application for an expanded gauge R&R. The only thing you have to remember is that in that scenario, when you go into the dialog box, test method now becomes a fixed variable rather than a random variable. So to get the proper analysis, you need to identify that, which is really very easy in Minitab in the dialog box. Your 3 different test methods or 4 or whatever you're doing is identified as a fixed variable, not a random variable.
Excellent. Well, that's it. We have a couple other comments I can share with you afterwards, Lou, and maybe some attendees will be able to contact you by email and carry on some discussion. Otherwise, thank you again for presenting with us today, and I hope everyone on the phone has enjoyed the presentation. We'll, of course, have more webinars coming up, which we'll announce via our LinkedIn group as well as by email newsletter. Those will typically come with a little more notice than this one. We had a little delay this week, but we'll certainly have others. Thanks again to you, Lou, and hope everyone has a great day.
My pleasure.